Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. Our series of episodes on time series have primarily covered univariate time series. That is, sequential data that is observed in a univariate or single variable value. That's not entirely true. We touched on some use cases for multivariate time series. But when you need to move out into an actual application, then you can often encounter real-world problems that weren't there in textbook data. A good example of this is unaligned data. In this episode, I interview Alex Terenin, one of the co-authors of the paper Aligning Time Series on Incomparable Spaces. We discuss their methods, which are inspired by optimal transport for time series alignment.
My name is Alex Terenin. I'm an incoming postdoctoral researcher at the University of Cambridge.
Well, before we get into a discussion of the paper, tell me a little bit about what you have planned for the postdoc.
Mostly my plans actually are going to be to work on similar topics to what I've been doing in my thesis. In my PhD, I've done quite a bit of work on decision-making systems and Gaussian process methods. The paper that we're talking about actually is sort of like a side project, at least from my point of view. And so that work, I've had a lot of success with it, but it feels more at a halfway point rather than a completion point. What I'm really planning to do is kind of develop a lot more of that and build on the ideas. So I'm really excited. Well, I was supposed to start tomorrow, but I think probably that's going to get postponed a little bit. I'll probably start in about a week or so. I'm very excited.
Well, the paper I invited you on to talk about is titled Aligning Time Series on Incomparable Spaces. You'd mentioned this as being a side project. How did you connect with your co-authors?
The first author on the paper is Sam Cohen, and he is a lab mate of mine. We have different affiliations on the paper because my advisor, who is Mark Dyson-Roth, switched universities kind of midway through my PhD. Sam is really interested in optimal transport and in particular in applications of ideas of optimal transport for tackling various problems and building tools for machine learning. And so I got involved in the project because he had this idea for extending something called a Gromov-Wasserstein distance, which maybe we'll get to in a bit, to a time series setting. And needed basically just somebody who had like a little bit more experience with the mathematics and the analysis, as well as with the process of actually putting together a scientific paper, because this was one of the first kind of works that he did during his PhD. When we got things to work, we decided to write together. I also want to credit the other authors on the paper. This is a joint work with Julia, who's not in our lab, but in kind of one of the labs sort of around ours at UCL, as well as Brandon, who's at Facebook Research. He does a lot of work on how to differentiate through interesting things. So that's kind of the team and how it got together.
For listeners not familiar with optimal transport, can you give a high-level overview?
So optimal transport is a very intuitive thing that ends up actually being mathematically very rich and you can build a lot of things out of. Imagine you have two piles of dirt with the same amount of dirt lying in each pile. I'm talking about literally you have like a pile of sand that's sitting on like a bit of concrete or something like this. And you've got two of these things, and somebody just tells you that they have the same amount of sand in them. So the question is, how do you move the sand from one pile to make it like the other pile in a way that minimizes transportation cost? And I've kind of stated it with sand lying on a thing of concrete because it's a very easy image to picture in your head. But you can also think kind of a bit more abstractly where on one side you have like consumers and producers, or you have a more like economics type sort of way of thinking about it. So what optimal transport is the study of this class of problems and how to formalize them mathematically and what kind of concepts you can actually build out of the formalism once you have it. One of the key concepts that you can build using optimal transport is a notion of a distance. So for example, if you have two different piles of sand with two different shapes, let's say one of them is sort of like a long and narrow shape and the other is more like just a big blob because the sand is arranged differently. You could actually say, how far away is one pile of sand from the other pile of sand? And this is done very easily. You just transport the sand from one pile to the other one in the optimal manner, which minimizes the transportation cost. And you ask, what is the total cost that you pay by doing that? And so it's really easy to draw. It's very intuitive. And that's the idea of optimal transport. The thing I just mentioned to you is something called the Wasserstein distance, is sort of constructed in this way.
Well, I like the sand analogy. When I think of grains of sand, I'm thinking of something fungible. I'm not concerned with this grain versus that grain. And in that sense, if I have two piles, it seems like there's an operation here of how many grains of sand or the minimum number to take shape A and convert it into shape B. Is that a fair stretch of the analogy?
Yeah. So basically, the pile of sand, you're right, that the sand has kind of a discrete shape in it. And you're also completely right that we don't distinguish between different individual particles in the sand. It's not like we have sand and different particles of sand have different colors and we want to do some kind of thing with the colors. There's nothing like that. All of the particles are identical. In the example I've given you, you can think of it as like a discrete number of particles, but the abstract theory allows you to have essentially a continuum of particles, and sort of the discrete nature that is important in the example actually doesn't really play much of a role in the abstract mathematical setup. It's one of the things that makes it quite a powerful tool.
With something being generalizable in that way, it obviously has a lot of mathematical applications. I'm curious, are you aware of any industrial or maybe econometric applications as well?
I want to say absolutely. These ideas, now I'm not an expert, but I know that in operations research, people will use this stuff. And in like various flavors of economics, how to like arrange stuff, people would use these ideas. But it also ends up in machine learning being like a really useful tool for just as like a technical tool for building components of generative models. And so this is kind of almost straight to the examples that we have in the paper, which is generative modeling. As I mentioned, optimal transport can be used to define notions of distance. And those notions of distance, in turn, can be used for building losses. So if you're training a model and you want to have an interesting kind of loss that's tailored to the domain and incorporates whatever, some kind of structure from it, for instance, a geometric structure, then optimal transport can actually be a tool for building such a loss. But this is within machine learning. I guess you were asking me more broadly. But more broadly, they are definitely used as well.
Well, I like the application of machine learning. If I'm going to train a model, I need a loss function that's going to be efficient. Are there any computational considerations when adopting this approach?
Yes, sometimes. And that's why we write papers about this subject in part. Because the optimal transport distances are kind of very rich sort of things. So you need to, generally, there is an algorithm that is used to actually compute the distance. Typically, there's many variations of this, but the sort of magic two words to know about, which is a Sinkhorn algorithm, which is sort of an idea for essentially giving an algorithm that is quite efficient for computing these things. If you need to run an actual algorithm to compute your loss, you might ask, well, what am I going to do? How do I differentiate through that for purposes of like training or minimization? And that's actually something else that there's a whole like list of papers written about. And it's closely related to, for instance, differentiating through convex optimization problems. And so I just want to plug Brandon Amos has done a whole bunch of work as part of his thesis and other things exactly on this topic, which is if you have some kind of optimization problem or some kind of algorithm that's used for computing a loss and you need to differentiate through that efficiently, can you do better than just literally unrolling your computation and just backprop straight through the whole thing? And oftentimes you can do a bit better than that. And so this is kind of something that people study. But I do want to mention that these things do end up oftentimes practical. It takes some actual like effort to compute the loss. I mean, you don't just summon square stuff, for instance. The fact that you have to do more computation there doesn't really kill the ideas.
Well, there's another prerequisite we should probably go over before getting into the core contributions of the paper, and that's dynamic time warping. Could you give another definition?
Dynamic time warping works as follows. We have two time series, call them X and Y. The key thing here is that the time series are defined as a sequence of discrete points. So we're not talking about an actual continuous curve. The inputs going into this thing is a finite sequence of points, potentially of different length. So we might have one time series that is sort of sampled with like more points than the other time series. We want to align these time series as much as possible with each other. This is something that's actually very similar to the optimal transport problem, because remember that in the optimal transport problem, we have two piles of sand, and we're essentially aligning different grains of sand with each other in the way that minimizes the cost. Dynamic time warping is something that's a lot like this, except in the case of the sand, we sort of assume that there's no sort of structure with the individual grains of the sand. There's no color, as I mentioned, I think earlier. There's no ordering. And here we're going to change the problem in order to actually have an ordering, and we're going to enforce the ordering. In the time series case, there is an actual order to the points. And so it's a very similar problem where we try to align the points to each other, but we enforce the fact that the ordering of the points remains the same in both cases. And so the first point in time series 1 has to be aligned to the first point in time series 2. And the last point in time series 1 also has to be aligned in time series 2. And so the question is, how do we arrange the sort of middle points as accurately as we can? Because the problem is discrete, you can represent each alignment as a matrix. What you do is you build a matrix where the amount of rows is the amount of points in the first time series, and the amount of columns is the amount of points in the second time series. And you just put a 1 if the two are aligned, and you put a 0 if they're not aligned. And so you have a little diagonal of 1s that starts from one corner and gradually moves up to the other corner. And we call something like that an alignment matrix. And so for each alignment matrix, there's a certain cost. Dynamic time warping, you get a distance by basically picking the alignment matrix that minimizes that cost and then looking at the number that you get. So that's dynamic time warping.
So quick follow-up just to make sure I understand. I'm thinking of maybe two of those old-timey movie cameras that have the hand crank. So, of course, there's a lot of variance in the rate at which observations are being taken. And if maybe we have two of those cameras from different angles and also different rates, lining that up, is that something this technique can help us with?
What's the data? Is it the images in each camera?
Yeah, I guess it would really be the time series of the images taken.
Yeah, but I mean, what's an individual point in this time series? Is it an image, or is it some kind of number that represents where an object is, like from the point of view of the camera? So you've already ran some kind of other thing to get that, like...
Good point. So yeah, let's say it's the position of an object that you can see from both cameras. So you're looking for an X, Y, and a Z. So
if you imagine you have two cameras that observe an object, and there's some kind of method that sort of runs over the image and gives you back a position of the thing relative to the camera, then in a sense, the thing that we're trying to work with is exactly that. You have two time series of an object moving, but it's from different cameras, and so the actual numbers representing the position are going to be different because the camera angles are different. Aligning those things with each other is exactly what like DTW and Gromov DTW is trying to do, with the extra point that it can also do that even if one of the cameras is recording faster than the other. So let's say one records at 24 frames per second and the other one is like a fancy camera records at 48 frames per second. It could also align those for the same length of time.
The following message comes from DataIQ, the platform for everyday AI. Let's face it, the potential for positive change with AI is huge. But seeing that value is hard. AI-driven growth is about organizational transformation, not just technology. And today's businesses struggle with the complexities of bringing AI innovation to fruition. That is where DataIQ comes in, infusing a culture of working with data and AI every day and at every level of the company. Whether solving for the mundane, like automating forecasting, or what is the optimal number of widgets to buy, or understanding moonshots that push the limits of today's technology to grow your organization and innovate. That's Everyday AI. Join more than 45,000 people worldwide across banking, insurance, pharmaceuticals, manufacturing, retail, and more who are driving results with DataIQ. Visit dataiq.com to learn more. That's dataiku.com. VPLS is a managed service provider and managed security provider with a 20-year history of industry-leading customer service. VPLS's network and security operation centers can be an additional resource for your IT team or function as an outsourced IT department. They offer help desk, managed security, managed backup, and other managed IT services. They handle the IT needs of both large and growing companies and can help your team with IT needs of all sizes. They operate 24/7, 365. Who else does that? Maybe they're a good fit for after-hours support for your team. When it comes to things like cloud migration or backup and disaster recovery, you're going to need outside expert help. VPLS is a great fit for companies with existing IT staff and teams, but may have some gaps in their IT framework, which could include cybersecurity, network optimization, and more. They're great for companies without existing IT support who are looking for experts to manage their entire IT infrastructure. And they're great for companies looking for IT expertise for a specific project or issue. Visit vpls.com/goit to see all their offers, including a low monthly co-location rate for new customers. That's vpls.com/goit. Let's get into some of the core contributions of the paper, perhaps starting with the distance function you're proposing.
I mentioned how dynamic time warping works earlier. And so one of the key aspects about it mathematically is that it's defined as the minimization problem over a series of alignment matrices of a cost. In optimal transport, that's exactly the same, only you minimize in the case of a discrete probability distribution. So you're aligning a pile of sand with sort of a finite set of, let's say, categories, like let's say bins, rather than with, something sort of continuous. And so there, it's the same problem, only instead of alignment matrices, you work with coupling matrices. And a coupling matrix is essentially exactly sort of the same thing as the alignment matrix, only without the time ordering. It's also something that's got entries between 0 and 1, and rows correspond to one of the probability measures. I'm using the word probability measure as a replacement for pile of sand, and the columns is sort of the other probability measure. One of the really cool things about the sort of optimal transport problem is that you can generalize it to other settings that are not quite the same as the classical setting. And one of those is what's called the Gromov-Wasserstein setting. So Gromov-Wasserstein essentially generalizes the Wasserstein, which does not require the two probability measures to live on the same space. So instead of having two piles of sand that both live on the same block of concrete, you might have a pile of sand that lives on the concrete on one side, and then you might have something else like an image, taken by a camera on the other side. Or you're not going to have a single image, you're going to have a big collection of images. And so the question is, how in the world are you going to try to compare two things like that? They're sort of completely different, that have nothing to do with one another. And the answer is, you don't compare the spaces, you compare the relationships between the points inside the spaces. So in the case of the pile of sand, instead of thinking about all of the pieces of sand as having like just some location, if I have a finite number of points, I can build a matrix which looks at the distance between any 2 points in the pile of sand. And I can just build a big matrix that tracks all of those distances. Similarly, if I have like a collection of images that describe some kind of phenomena that I think is related to the sand, and I have a collection of images, then I can build a big distance matrix between those images just the same way that I build a distance matrix between the pieces of sand. And so now I have two distance matrices, and I can just ask how far away are they. And the formalization of that idea is the Gromov-Wasserstein distance. What it captures is essentially the kind of intra-relational geometries, as we call them, between the two sets of samples and the two spaces. What is Gromov dynamic time warping? It's exactly this idea, but where we build the time structure in the same way that we did it for alignment matrices. So I can give an example straight from our paper. Figure 3 has something called the quick draw data set. Now, the quick draw data set is, somebody took their kids and they had them draw some sort of different shapes. So they had somebody draw some shapes of hands, somebody else draw some shapes of fishes. I think clouds and blueberries are the other two categories. Different points in this data set have a different number of discrete observations because in some of them they're drawn faster than in other ones. And something you might be interested in doing with that data set is finding, okay, can I just pick one example that summarizes the data set? Can I find some kind of mean in this sort of crazy space of handwriting sequence time series? And the answer is you can. And so one of the things that methods like dynamic time warping and actually optimal transport methods also allow you to do is they allow you to have notions of barycenters. Now, a barycenter is like a mean, but a mean is something that you have of real numbers, whereas a barycenter can be something you can have of something much more complex. Images being kind of another example, although images not being a good example because points on a sphere being like a much better example, because if you just take a bunch of points on the sphere and you try to just take an average, you're probably going to end up with a point that's not even on the sphere. Whereas if you take a barycenter, you will get a point that is on the sphere and, is sort of a center of the points that you've chosen. Because optimal transport gives you ways of defining these notions, our paper essentially gives you a way to extend those ideas to the time series setting. And so if you look in figure 3, you can see with DTW, you have basically an average shape of a hand or a fish. And it actually doesn't look very good. How come it doesn't look very good? Well, it's because in the data set, you also have symmetries. Some of the hands and some of the fishes, they're going to be rotated compared to each other and translated and kind of moved around the space. And so one of the things that Gromov DTW allows you to do is get a notion of an average for this data set that is based off of comparing the distance matrices that I described earlier for each observation. And then you just pick the point that has sort of an average looking distance matrix. And so if you want to then draw such a thing, you sort of pick a point and then you draw the other ones to match that. And so that's roughly how that works.
Is picking that point trivial or are there some steps involved?
I believe we did in the paper was
we draw the sequence by applying a multidimensional scaling algorithm. Specifically, we use the one in scikit-learn on the distance matrix associated with the barycenter and then display the result.
So I think the answer is in that example that we don't generate the time series. We just pick the time series whose distance matrix is the closest to the one that's the barycenter. I don't see anything else that's sensible that we could have done in that example, at least. One of the really cool things about having a notion like GDTW, which again gives you a way to compare points in potentially different spaces by containing the time series in different spaces by comparing their interrelational geometries, is that once you have such a notion and you know how to differentiate through it, you can use it to build a generative model. So in a Wasserstein-GAN, you have basically a loss that's used to train the generator and the discriminator. That loss comes from an underlying notion of a distance that needs to be selected. And so all we do is end up using GDTW as this notion of distance, together with an entropy regularization term, which is needed sort of for the method to work algorithmically. It sort of just smooths everything out a little bit. What you get ultimately is an objective that looks like the minimum. So the minima with respect to the parameters of the neural networks of the expectation with respect to the generator of GDTW. That is a loss that you can define. And once the loss is defined, as long as you have a way of computing it, which we can do with a sort of Sinkhorn type algorithm, and you have a way of differentiating through it, which we also do because the inner GDTW term, we actually use the softened version that has good properties with respect to differentiation, then that's something that's defined. And so you can just try to solve that problem using your favorite optimization algorithm, and you'll get a set of neural network weights, and those weights in turn will generate time series. So you get a generative model. But a typical application area for methods like this is actually imitation learning. So in imitation learning, there is some kind of expert data that we have some kind of system, and the goal of the system is to imitate the expert. It's kind of a very intuitive name. In the time series settings, the expert might have like a trajectory of some kind of problem that, you might otherwise be using reinforcement learning for. We're not using reinforcement learning. I'm just using that as a kind of word to be evocative of the sort of setting we're thinking about. So actually, an example of this is in figure 5 in our paper. So in figure 5, there is a car that sort of drives in a spiral shape. The expert is somebody with a video game controller probably who's driving that car. And what we observe is actually the images that are in the top row. So we observe an image of a car kind of driving around sort of in a spiral shape. And the goal is to learn, not in image space, but in XY space, a policy of an agent that generates the same trajectory. And so we use GDTW to solve that problem. Now, one of the really cool things about like that setup is that if we just give you the XY coordinates of the car, then you can solve that problem by just dynamic time warping. So you just find the policy that leads to trajectories that minimize DTW. The really cool thing is that you can take this sort of procedure where you just take a policy with an agent, you sort of run the policy, and you try to minimize the DTW between the trajectory that the agent produces and just the example trajectory that you saw. It's kind of a very basic imitation learning type setup. You can more or less solve this problem with DTW. But what DTW can't do is you have an expert that gives you images, and you have a policy that doesn't produce images. It produces trajectories in R2. And so GDTW essentially gives you a way of doing that, which is you take your agent, you run the policy with the agent, you get a set of numbers in R2, and from those numbers you build the distance matrix. Then you get a sequence of images, which are just pixel data. From that pixel data, you build your distance matrices. That's the expert's distance matrices. And you just sort of minimize GDTW, which is built out of those things. And you get a policy for the agent. And we actually didn't compare the method against any baseline because we were, at the time of writing, not aware of any baseline for actually doing this particular task, where there's both kind of an imitation learning setup and a time series setup. But it's also an area where optimal transport is often considered in sort of many variations.
Do you have any thoughts on where this line of research should go next? I know you may be off onto other topics, but I'm curious if you have a vision for what comes next.
So optimal transport for machine learning broadly is a very active area. There's a lot of work being done on both exploring the different variations of the setup. And one of the contributions we had was exploring what happens if you add a time series structure to kind of the setup. But there's also a lot of work being done on kind of the algorithmic side as well as the application side. I think people in the community are becoming aware of these tools largely through just sort of a lot of papers being written about them and can use them for various problems in areas like robotics. I think there's a little bit of sort of image processing, although nowadays image processing is mostly done using other stuff. Really, the goal of broadly the community is just development of these things as a toolbox that you can use for whatever your purpose is. And the toolbox is in pretty good shape. I mean, it's certainly not an area that's finished. There's still a lot more to do.
Can you comment on how computationally demanding these approaches are?
So anytime you have a loss that is built by like some kind of algorithm, you generally, if you can, compute the gradient of that loss without running a second algorithm, that's useful because it means that all you need to do is just solve the original minimization. You don't need to backpropagate all the way through it. And that sort of can save you compute time, it can save you memory, and it's cleaner. So in TensorFlow and frameworks like this, there is a functionality for defining custom gradients. that is exactly based for this, where, you can take a certain shortcut for computing the gradient that otherwise you'd have to do some kind of massive computation. So the advantage of this really simple formula for the gradient of GDTW is that it saves you potentially your compute costs. You just solve the minimization without any kind of backprop. And then you take the solution, you plug it in. And so the rest of your, back propagation for your neural network, sort of whatever it is you're doing, becomes isolated from the computation of the loss itself. It's both cleaner and it's more efficient. And in particular, it saves you memory. Because if you have to store the intermediate result of 1,000 iterations of an algorithm in order to differentiate through it, you might run out of memory doing that. But a sort of shortcut formula like this prevents you from running out of memory because you never have to store all the intermediate steps to begin with. You just need the final solution. This is actually typical behavior, not only in GTTW, but also in a whole host of other examples. And so if you see papers about differentiable layers or differentiating through convex optimization, they're often studying this idea in sort of different settings than ours. But it works in our setting as well, and that's one of our results.
That's a good trick. Yeah, there's a number of innovations in the paper, and I hope listeners will check it out and learn more about the work there. Alex, before I let you go, I'd love to switch gears for a second. I know one of your primary areas of interest is Gaussian process models. What should listeners know about them?
So that's a very different topic than the one we were talking about. And it's kind of the bulk of my work, so I'm quite happy to plug it. Broadly, the main thing I would say about Gaussian processes is just for people to be aware of them. Gaussian processes are a way of handling uncertainty that is sort of very principled and works really well for both problems in spatial statistics and as well as decision-making problems and settings like Bayesian optimization, where sort of principled handling of uncertainty is really important to balance, explore, exploit trade-offs and other things like this. And so I don't have any kind of particular message about them other than it's a really cool set of techniques. It's a lot of what I've been working on recently. And I'd love to talk to you more about them because it's a subject area sort of I've spent a lot of my time on.
And where can people follow you online?
At my website, it's avt.im. People can also follow me on Twitter. And by the way, the website has blog posts for both this paper and others. So if you want to read a kind of bite-sized description of what's going on in the paper and just see some, pretty pictures, then the website will have those. It's also got a nice video of basically some of the alignments. So you can see how the time series alignment under DTW and GDTW changes as you kind of move two sets of time series around in space. And I'm also active on Twitter. So my Twitter handle is AVT_IM. So it's just like my website with an underscore instead of a dot. And I'm actually writing my PhD thesis, which I mentioned Gaussian processes briefly, which is sort of the main topic of the thesis. I'm actually writing my thesis in an open source format that anybody can read and look at while I write it. And I'm actually due to submit very, very soon. So the thesis is close to complete. And yeah, just, go on GitHub, check that out. I'll have a pre-compiled version of it available soon because Overleaf is becoming very slow compiling the thesis. And that makes it a bit difficult for people to get to as it's gotten quite long. But it's there. Feel free to check it out. Feel free to follow me. Feel free to send me an email.
I'll have that in the show notes as well so people can find it there too. Thank you so much for taking the time to come on and share your work.
Thanks for having me.
That concludes another installment of Data Skeptic Time Series. Our guest today, Alex Terenin.
Thanks to our sponsors, DataIQ and VPLS.
Myself, Claudia Armbruster, as associate producer. Vanessa Bly, guest coordinator. And our host, Kyle Polich.